Good day, my geometry students. Today we get to look at the third section of chapter 15, where today another section that's relatively easy. And if you like the last section, you're going to love this section. Okay, it's relatively easy. What we're going to look at today is we're going to talk about tangents. Again, in this case, the tangent we're talking about here is not the trig ratio we talked about in the last chapter. Okay. So tangents and circumscribed angles. Now, the back of your brain, you should be start thinking, I remember doing circumscribed angles. Well, we're going to see how that's applied today. So the essential question that we're going to deal with today is what are the key theorems about tangents to a circle? Now, this whole section really just deals with application of the theorems. Like I said, it's very easy. I'm not going to do much proofs. So I'm just going to go and just cover the key theorems. The first thing we need to talk about is what do they mean by tangents, and then we'll look at what do they mean by circumscribed angles. So if you take a moment here, I've highlighted something here, but it's relatively easy to deal with. If we have a circle here, and we happen to put a point on the circle and we just draw a random line through it, okay? This line right here that touches this point, this line right here is called a tangent line. It is tangent. It touches the circle at a point, and that point that they touch is called the point of tangency. So, and what we're going to do leading up to is that, once again, this is a line. It's like y equals mx plus b, or ax plus by equals c. It's a line, okay? Algebra 1 concept of a line. Where it touches, that's the point of tangency. All right, now that is what they're talking about in this part. Now again, they have the Explorer for you to do, but I am not going to waste your time on that because it's relatively easy. The next thing we want to do is they're asking us to prove the first theorem, but we're not going to prove it. We're just going to talk about it. So the tangent radius theorem, and it's really easy. It says this: if a line is tangent to a circle, again, we did this before in the previous page. Here we have a circle. We have a point of tangency. There's a line that goes and touches the point of tangency. So if a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. So if I take my radius and connect it to the point of tangency, this creates a 90-degree angle. All right. Again, now the diagram is using it up here. You could do anywhere you want, but just as another way, if I have a point of tangency here and I draw a line here, once again, that radius to the point of tangency will create a 90-degree angle to that tangent line. All right. Now they got a couple of examples. I am not going to waste your time with that because, like I said, a lot of this is just pretty much common sense. The next page is just the converse. You don't use that too often in this section, but again, it has to tie into all our theorems from previous chapters. If you have a theorem, you can always find its converse. All right, now the next one is proving circumscribed angle theorem. Again, I am not going to prove it, we're just going to associate it, okay? Here is the circumscribed angle theorem. A circumscribed angle of a circle and its associated center angle are supplementary, all right? Like I said, this is really easy. I have a circle. I have 2 points of contact, okay? We have 2 tangent lines. They connect at a common point. And what this whole thing says, well, we already know in the previous theorem that we know right here that is going to create a 90-degree angle. And we know right here it's going to create a 90-degree angle. And what this theorem is telling us is very simple. This circumscribed angle, once again, is the angle outside the circle. And from section 15, the first section, this is your central angle. So it says if we know the circumscribed angle, we can figure out the central angle because they're supplementary. The sum of these two angles have to equal 180. Or if we know the central angle, we know we can find the circumscribed angle by using the supplementary angle. That's what I'm saying. This is not a hard section. Now, based upon looking at this section, there's hardly any your turn. So what I'm going to do is take and look at some of the even problems in your homework and show you how easy it is. Look at problem 6. We're given that again, this is multi-step. That means first thing they want us to do is find the length of each radius, identify the point of tangency, and write the equation of the tangent line at that point. Now the problems they're giving you here are relatively easy. If this was a upper level, like a course in college, they won't give you simple equations. They'll probably give you something with an angle on it or a different slope. So looking at number 6, well, the radius is 2 units. Again, you can do it by just, in this case, just looking at the diagram. Here's the center, here's our circle, and we can determine that the radius is 2 units on either side of the center, so the radius is 2 units. Point of tangency, that's this point right here. Again, simple pre-algebra, algebra, x is 3, y is 4. And then the line part is they're trying to find out the equation of this line. This is a horizontal line, and it's going to be y equals 4. Now, I could have took the time and used the point slope form and done that, but again, it's just common sense. All right, that was number 6. Now, number 8, again, remember, don't let the diagram or information throw you off, okay? They're not that hard. Just think it through. Here we have a figure. We already been told that QS is 5. That's this segment right here. QS is 5, and also it says that RT is 12. All right. And we know that RT, the line RT, is tangent to the radius QR, right there. There's the point of tangency at R. With the point of tangency at R, we want to find QT. We want to find this length here. Don't let it throw you off. We're going to have to go back and use some old rules. Again, I'm going to use the Pythagorean theorem. The reason I know I can do that is because R is a point of tangency. That means this line RT is congruent to, it's perpendicular to QR. Again, if you look at it, it creates a right triangle. So again, we want to find the length of QT. And if you stop and look at it, we're going to use the Pythagorean theorem. Because if you stop and think, if we know that QS is the radius, guess what QR is? QR is also the radius, and since QS is 5, QR is going to be 5. So we can use the Pythagorean theorem in this problem. And that's what I did next. Again, what I did is I took the Pythagorean theorem. Once again, it's a squared plus b squared equals your hypotenuse squared. And I just applied that. Like I said, these are not that difficult. You just got to step back, identify, label, think it through. All right, now let's go to the bottom part. The segments in each figure are tangent to the circle at the point shown, and our job is to find each length. So here is our diagram here. And we are being asked to find this length of R, okay, this length here and this length here. All right, now don't let them throw it off, okay? We already know that these are going to be very simple. So if you look at this problem right here, we see that SR and TR are tangent lines, okay? And then since they are tangent lines and they connect here, right off the bat, you're going to notice, based upon, there's no really theorem on this or rule on it, but you're going to know that this side and this side are congruent. So they're congruent, and all we got to do now is set it up by, we know that y squared over 7 has got to equal y, and we have to solve for y. Well, again, I didn't fill this one in. I thought, let's just take the time to do this. It's relatively easy. So the next thing I'm going to do is I'm going to cross multiply. I'm going to multiply both sides by 7. Then I'm going to put it into the form of a quadratic. I'm going to set it to equal 0. All right. Again, this is going back to Algebra 1. The left-hand side is, we're going to factor out a coefficient of y squared and 7y, which is y. Okay. Now we have it in factored form. So now we're going to go apply the zero product property. So that means the factor y and the factor y minus 7 have to equal 0. So y equals 7, y equals 0, and y minus 7 equals 0. And then we go ahead and solve for y. Well, we already know that y can't be 0 because we got a length here. So we know that y is 7. So that means the length here is 7. So the length of SR is 7, and the length of TR is also 7. All right, don't let these throw you guys off. They're relatively easy. A couple more. Some of these, they give you a lot of space. There's not a lot to do. All right, here we go. PR is tangent to circle Q at the point of tangency of R. Here we go, right here. And PS is also a tangent line to the circle of Q at S. And we want to find the measure of Q. Again, I probably need to use a different color here. We want to find this angle right here. Well, if we go back and use the circumscribed angle theorem, we know that angle P and the angle of RQS, or just the angle Q, they are supplementary. Okay, so all we got to do, it's very simple, is take 180 degrees, subtract from that the angle P, firing up our calculator. We will find now that the measure of angle Q will be 138 degrees. That is how you would do that one. And then one more. Again, they start throwing more stuff into the problems. Do not let it throw you off, okay? Just pick it apart and think it through. We have a circle. We see that PA is tangent to the circle at point A. We also see that PB is tangent at the circle O at B. And we notice that the measure of angle P is 56. Use the figure to find each measure. So what they want us to do in this case is, I think in this case, the one they're asking us to do is find the measure of AOB. So the measure of AOB, and this one is just like that previous problem. So we can use the circumscribed angle theorem. So it's 180 degrees minus 56 is 124. All right. So that is pretty much what section 3 of chapter 15 is all about. Just tying into it several theorems. This one is an important one, the circumscribed angle theorem. The inverse one, or the converse one, is no big deal. It's part of geometry. This one right here is just gives you a definition of what's really happening. And then here is the beginning part. So we got our key theorems now, where we can take a circle and a tangent line, and we can find other lengths of other sides, lengths, or the measures of any angle. Again, you may have to use some previous stuff from previous chapters. They all build on each other. All right, guys, glad to get to talk to you today. That's section 15-3. Catch you later.